The next example we're going to do today has to do with the minimum area of steel and the largest cross-section possible, and the maximum amount of steel and the smallest cross-section possible. Right? Now, when we say largest cross-section and smallest cross-section, that means that the only thing that you're changing is the height of your cross-section, the depth of that cross-section. Okay? So in other words, the width has to remain the same, the properties have to remain the same, because there will be different solutions if you change either the properties or the width. Mm-hmm. So for a given width and a given set of properties, that means strength of concrete, right, and rebars, you will have one kind of solution for smallest section and one solution for largest cross section. Okay? And as shown here in the graph that we have been using for a while, right, notice that we have then this line which represents your tension control case, and that's the one that will give you the smallest cross section, because at that point is where you're putting the maximum amount of steel, right? If you put the maximum amount of steel, then that means you don't need a very large section to carry the moment. So your depth can be smaller. Mm-hmm. On the other end is the AS minimum. So you put very little steel, then you need a very deep section in order to create the moment capacity. Right? And that's where you get your largest cross section. But between these two numbers, there are lots of solutions. Okay? And so that's what we are going to do in the next example using procedure B. So let me find that example here. Here is the example. So let's see the beginning of the example. All right. So now you have then a simply supported beam, 20 feet long, carries a maximum moment of 465 kips feet, includes a beam weight already of 0.85 kips per foot. If the width of the beam is 18 inches, F prime C 4,000 and Fy 60,000, and you're using number 4 stirrups, determine the largest section, okay, the smallest section, and then a section where epsilon T is 0.01. Okay. So largest section. You know? So as we said before, the largest section, the practical size corresponds to the minimum amount of reinforcement. Larger cross section, then a minimum amount of reinforcement. So we go to the formula for minimum, right? And instead of using AS minimum, we're going to use rho minimum. Why we're going to use rho minimum? Because when we use procedure B, remember, we replace the area of the steel by rho BD, right? And because of that, it's best to work then with rho, so that we keep it consistent and we do the same thing over and over. Okay? And so this will be then looking at these two values, of course, because 4,000 is less than 4,444, then this number controls your minimum value and you use it. And then you take your regular inequality, right? And your design strength, you replace the parentheses by 0.9D, and you're also going to substitute the AS by rho BD, and that changes now your equation to look like this. Now the good thing here is that because the B is given, remember I said there will be a solution for a given B. If you change the B, you get a different solution. Okay? So now the only unknown really is your D value, because you know your rho value is your rho minimum, right? Your phi factor is going to be assumed as 0.9, so you're given the moment, so everything is known, so the only thing you need to find is your D. So in this case, my D happens to be 43.8 inches. I assume one layer. This is minimum amount of reinforcement, so that will be very, the number of bars will be minimum too. So that means I don't need two layers, so one layer will be alright. So that adds to 46.3. Okay, here is, where you want to go to 48, that's fine. I decided just to simply use 46. Okay, that's just the decision. And the other reason for doing that is, remember that 46.3 really is your maximum, right? And so you go to 48, well, you are exceeding your maximum, right? And the amount of steel that you're going to put is going to be even less than the minimum. But you cannot do that. You can always have to put the minimum. So that meaning that you're not doing an economical solution. So you have to go, in this case, below the number that you find, because 46.3 represents the maximum depth. Okay? That's how high you can go. Okay? So you pick something a little less in this particular case. So we got the value. We don't know how good it is. Do we have to check deflections or not? I don't know. So the first thing I need to do then is check that my H value that I got here satisfies the table 9.311 in ACI, right? To see if I need to do deflections or not. Well, for a 20-foot simple supported span, we use L over 16 here, and that will give us a value of 15. Well, I'm using 46, so that's plenty of capacity. I'm going to check my beam weight, and I got 0.863. Well, my value is 0.85. That was the assumed value, so we're close, really. Mm-hmm. So we don't need to worry about that, right? Now you have a big difference. You just redo the calculation one more time with a new weight, okay? But that's all. And I already showed you how to do that calculation again, so you have an example already how to do that. Okay, so now I'm going to find my D value. So 46 minus 2.5, 43.5. I multiply that times 18 times my minimum amount, so I get 2.61. I look at my tables of what I can use, and I find something pretty close, 264, was not bad. Number 6 is, the B minimum is 1475, right? And I'm having a B value of 18, so it fits within that. Now, how do you find this number? No? For those that forgotten, remember you have to go to your design aids, right? So B minimums are here, right? Minimum width, right? And so we're using 6 number 6s, and that requires 14 inches in order to fit it nicely. But because you're using a number 4, you need to add 0.75, so the value becomes 1475. Mm-hmm. And so 1475 is your B minimum, and you have 18, so you're good. Now that we know the bar sizes, I'm going to find my actual D and D sub T using the size of the bar that I found. So it gets 43.63. So a little bit more than this 43.6. Right? My rho minimum should be okay. Yeah, it is pretty much almost the same. Right? And then I find my A value with the area of steel that I selected. Find my C value. Check for my ductility, right? So find my epsilon T. That means pretty good, 0.04. Right? For grade 60, we know that the tension control limit is 0.005, so this is a lot higher. So we are satisfying that pretty good, all right? So that means A is maximum is satisfied. Makes sense, right? Because we are at the other end, where in the A is minimum. So we're not exceeding AS maximum. Phi has to be 0.9. Right? Now, you don't want to do again the epsilon t. You can do C over D sub t and compare it to 0.375, which is the value for grade 60, and you will get the same conclusion. So once you decided what your phi factor is, it's been verified, you go ahead and check that your design flexural strength is okay. So we replace the phi value, 0.9, area 264, steel 60 ksi, the actual D value, your A value, and I find that this value is greater than 465, so we're good. Okay? So that cross section of 18 by 46 with 6 number 6s is good. Okay? Next one, they want to find the smallest section. Okay, now we are at the other spectrum. That means we're going to put AS maximum, right? So how do I find the amount of steel for AS maximum? So don't forget that AS maximum is related to epsilon t, right? And so that's what you are going to find. And you're going to look for that epsilon t that corresponds to AS maximum, right? And that, again, let me show you that graph again one more time, because that's the important graph, right? Yeah. So your AS maximum is here. So it corresponds to an epsilon t of 0.003 plus epsilon ty. That is your tension control value, right? The strain corresponding to the tension control value. For grade 60, right, this becomes 0.005, right? For other values, you need to find it, right? But for grade 60, it's going to be 0.005. That will give you the AS maximum. Okay? So then, what we're going to do next is simply move to the formula that we have here that we've been using for procedure B. Remember, we're using that formula. Okay? And we're going to replace the epsilon t with the value corresponding to the transition. Exactly. See? Yeah, the transition value. And that will give me the rho that corresponds to the rho maximum. Now, if you happen to have a formula for rho maximum, this is a place, this is one of the places, right, where you can use that formula. You have it. Mm-hmm. But really you don't need it, okay? Because remember, the maximum amount of steel is always this formula when you have epsilon t equal to the strain value corresponding to the tension control. Okay? So that's all you need to remember. So same formula, you don't have to remember more formulas. This is the same formula that we've been using. All you have to do is replace the epsilon t with the value corresponding to the tension control limit. Okay? And you get your maximum amount of steel. But if you happen to have the formula, you're welcome to use it. Okay? That's fine. So again, I replace then the 005 because that's what it is for grade 60. And that gives me my raw value. This is the maximum amount of steel that I can put in there. Right? And then I can move on to the next steps. Mm-hmm. And so the same thing, right? I got my mu less or equal than phi sub n, replace the parentheses by 0.9d, and replace the area of steel by rho bd, and solve for the d value, because I know my b happens to be 18. My rho is given as 0.018. My phi factor is 0.9, right? And so we get now a D value of 18.9. Okay, we add to that 3.5. Why am I adding 3.5? Because I'm dealing with the maximum amount of steel, right? And what's going to happen with the maximum amount of steel? Lots of bars. So there is a chance. I mean, I don't know, right? There is a chance that I may go into double layer. So just to cover that possibility, I'm adding 3.5. So that gives me 22.3, right? And I use 22. Okay. So normally, I mean, you will add, say you will add 2.5, and so you added like an extra inch here. And so that's what I was able to go from 22.3 to 22. But if you just add 2.5, remember that this is the smallest size. So you have to go up, you cannot go down, right? But in this case, because I have a 3.5, I have a little bit there, right? So then I can do that, right? Okay, so check, but now this is the smallest. So now checking for the H minimum becomes even more critical because you're using a very shallow section. So check minimum H. Okay, we do the same. We got 15. Oh, but this is 22, so we're good, right? But notice that we got pretty close to that one, right? We check the weight of the beam. Now the weight is a lot less. Okay? So here again, just to review, I'm going to show you again how to correct for the new weight, right? So new moment will be your given moment minus the moment due to the assumed weight, which was 0.85, and then you add the moment due to the actual weight, which is now 0.413. So here is the given moment. I find the moment of the beam, and they told me that the beam weight was 0.85 because it's a dead load and multiplied by 1.2. Don't forget that, because this value, your MU, is a factor value. So your weight of your beam has to be multiplied by 1.2. So this gives me the moment due to the assumed weight of 0.85. The next one is the moment due to the new weight, and again, it is being multiplied by 1.2, right? Because you want factor values, okay? And so my new moment then is 438.9. Well, so notice that the difference between the 465 and the 439 is not significant, right? We're looking at what, 5% maybe? So it's a 5% difference. Even though your height has changed from 46 to 22, right? Almost half. Right? Okay, so you solve again, find your new D, 18.3, add that 3.5, you get 21.8. So 22 looks like a good number. Right? So we use that value. Find the required area of steel. So again, we're going to assume a double layer. So your D becomes 18.5. So this approximate area I'm getting here is based on my raw maximum. I had to use this value because that's the value I found, right? So I have to use this value. Don't change that value. Okay, this is the value of your area. So we got that, multiplied by B, multiplied by D, it gives me 6. Okay, with that, I go to my tables, and I have different options. I can do 6 number 9s, 5 number 10s, 4 number 11s. All these options work. You can use 6 number 9s or 5 number 10s. Either with the cracks are a concern. Otherwise, 4 number 11s will be acceptable, right? Remember, the more bars you put is to control the width of your crack. Controls better the width of your crack. But for construction purposes, the least amount of bars that you put is better for the workers, right? So 4 number 11s will be one solution that is more practical for construction. Yeah. All right. So once I selected that, my 4 number 11s, I found my actual D and D sub T. Check my rho minimum. It should be okay, right? I mean, I'm just doing it because I got to get used to always check it, right? But you know this is going to be satisfied because you're using row maximum, so it should be satisfied. Okay, so your row is pretty big compared to that one. All right, find your A value again, find your C value, find your epsilon T. So there we go, 0.0048, grade 60 reinforcement, the minimum is 0.005 to be tension control. Therefore, the limit here has not been satisfied. So that's the problem when you work at the extremes, right? A little deviation and you can be off because you're at the extreme, right? So this one, I mean, pretty close, but didn't quite work. So what I'm going to do is, instead of using the 4 number 11s, I'm going to use the 6 number 9s. And now my D goes a little bit higher. So from 19.3 to 1944. Okay. And then again, check my minimum, check my A, check my epsilon T, and I didn't do this right. Yeah, well, I got an epsilon T now that is bigger than 0.005. But you can see here that this value should have been 19.44. And so that would give us a little bit higher. So that's even better, right? So the new number should be then is 19.44. Oops, 19.44 minus 692 times 0.003 divided by 6.92. We get about the same, 0.00543. So not much difference. Okay, so it's about the same. So 0.0054. So not much different. But this value should have been then the last value that we assume here. Let me see when we're using another place. No, that's the only place. Okay. All right. So we have that there. That needs to be changed. So all right, so now we are good. Okay, we have satisfied our values, and then that design will be okay. Check my design flexural strength, and yeah, we're good. Okay, 442 versus 439. Okay. The next example picks a value arbitrarily between the two numbers, 0.01, right? 0.01. And so if I use value here of 0.01, right, my raw value is pretty close to that, 0.0111. Okay, so I got the raw value. Then I'm going to do the same. Okay, my moment is still 465. My mu D minus A over 2 replaced by 0.9D. My AS replaced by raw BD. And I'm going to solve for D in this case because my B is 18. Always assume 0.9. And so my D value is 2397. I add 2.5, one layer, and I get 2647. So I said 27. Check minimum H. We know that's 15. So we are okay. Check the beam weight. Yeah, it's less than the 0.85. So I do again my correction for weight and correct my moment, right? Don't forget the 1.2 that multiplies the weight of the beams, okay? Because the effect of the rest of the loads is the same. The only thing that's changing is the weight of the beam. Okay? So with that, I recalculate my D. I notice that now I can go to 26. All right. So, and you're going to use 26. So 26 minus 2.5 give me an approximate D. With that, I get an approximate area. And with that area, I go and find my solutions. You can go 6 number 8s, which in this case it fits in 18 inches, one layer, or 3 number 11s that also fit. For construction purposes, right? Not 3 number 11s is better. For controlling your width of your crack, 6 number 8s is better. So in this case, I use 6 number 8. Okay. So find my D and D sub T's. Yeah, they are the same. Check my minimum. It is good, so no problem. Check my A, my C, my epsilon T, pretty close to what we assume. Right? Remember, you will not get exactly the same number that you assume because the rounding on the dimension, the rounding on the areas, right? So you don't get that, but it's pretty close. Again, this compares well to the value for tension control for grade 60. And so we can use 0.9, A is maximum is satisfied, check the strength, and we have the capacity, right? So the 3 cases now are shown here. So there is the largest section with 6 number 6s, the smallest section with 6 number 9s, and the intermediate section there with 6 number 8s. Now between this one right here and this one, there are lots of cross sections, lots of solutions. Okay? The only way you're going to get one solution is if you put lots of constraints on your design. Otherwise, I mean, you have several solutions. Okay. So that is important to understand that you're not limited to just one solution. You have several solutions. And you will pick whatever is best for your design, right? For your floor system. All right, so I'm going to stop this one here so you can look at this one with calm and in more detail. All right.